Hello, my name is Dongho Kim. It's our pleasure to publish a perspective entitled Defining Spectroscopic Features of Heteroannulenic Antiaromatic Porphyrinoids in Journal of Physical Chemistry Letters. The co-authors of our article are Dr. Sung Cho, Jin-seok Yoon, and Mr. Kil-seok Kim, Min-cheol Yoon from our group, and Professor Dong-kyu Cho at Inha University and Professor Jonathan Sessler at University of Texas at Austin. The aromaticity is defined for planar, cyclic delocalized pi electron system with stable resonance energy, bond length equalization, and link current generation by an external magnetic field. The concept of aromaticity is somewhat ambiguous, although it is often used and useful in chemistry. In general, the indices for aromaticity can be defined in terms of energy, structure, reactivity, and magnetic properties. In our work, we'd like to make a relationship between aromaticity and photophysical properties of expanded porphyrins such as electronic structures, excited lifetime, and nonlinear optical properties. Expanded porphyrins can be synthesized by adding more pyrrole rings into porphyrin molecules containing 4 pyrrole rings and find application in molecular recognition, IR dyes, and so on. As we increase the number of pyrrole rings in expanded porphyrin, the most unique features can be found in the optical absorption spectra, showing a continuous redshift to IR region due to the elongation of pi conjugation pathways. The molecular systems chosen for our study are saphirin, cyclo-6-pyrrole, and rubirin, which are all aromatic molecules, and orangarin, rosarin, and amethylin, which are all antiaromatic molecules according to Hueckel's Poem+2 rule. The absorption spectra of aromatic molecules show relatively sharp porphyrin B and Q-like band. In addition, we observed fluorescence with a mirror image to their absorption band. On the other hand, the absorption spectra of antiaromatic compounds are quite broad without any fluorescence or very weak fluorescence. The simulated absorption bands, as marked by thick lines, are largely consistent with the observed absorption spectra. But for antiaromatic expanded porphyrins, there are optically dark states in near IR region based on our calculations by time-dependent density functional theory. The molecular orbitals of aromatic expanded porphyrin show nearly degenerate HOMO orbitals, but this degeneracy is split in molecular orbitals of antiaromatic expanded porphyrins. In detail, molecular orbital structures of aromatic saphirin show nearly degenerate Garade HOMO and ungarade LUMO with a different number of nodal planes. This feature allows computation interactions among 4 frontier orbitals, resulting in featured B and Q-like band as similar to typical aromatic porphyrinoids. However, in the case of antiaromatic orangarin, the overall shape and phase of molecular orbitals are similar to those of aromatic counterpart, except for the same Garade symmetries and the same number of nodal planes in HOMO and LUMO. Because of these distinct molecular orbital structures, at least 6 frontier molecular orbitals should interact in antiaromatic expanded porphyrins. Especially, a direct HOMO-LUMO transition is symmetrically forbidden, which appears as optically dark state in near infrared region based on our calculation. These states can act as a ladder state in the excited state energy relaxation pathways, resulting in much shorter excited state lifetimes as well as non-fluorescent behavior in antiaromatic expanded porphyrin system. As compared to aromatic saphirin, antiaromatic orangarin exhibits higher paramagnetic properties based on highly positive nuclear-independent chemical shift values and paratropic ring current generation with counterclockwise direction. In addition to the nuclear independent chemical shift values and induced link current as an index for aromaticity, we would like to propose that the two-photon absorption cross-section values can be used as a measure of aromaticity in a comparable set of aromatic and anti-aromatic expanded porphyrin. As a conclusion, the photophysical properties of anti-aromatic expanded porphyrin can be characterized by broad absorption spectra without fluorescence, ultra-short excited lifetimes due to the presence of an optically dark state, relatively small two-photon absorption cross-section values, and strong paratropic link current generation. These common features of anti-aromatic species mainly originate from the unique electronic structures as demonstrated by molecular orbital analysis. Overall, methods described in this perspective are suggested as useful means for probing and codifying the electronic features of molecular aromaticity in expanded porphyrins as well as more higher annulene system. Thank you very much.